The topic I'd like to share with you at our today's workshop is wireless technologies in IoT projects with distributed computing. Nowadays, a large number of projects are based on the use of the Internet of Things. To make it simpler to comprehend, I'll use the abbreviation IoT from now on. When it comes to creating projects based on the use of the IoT, wireless sensor networks are often used. The purpose of our work was to analyze possible options for wireless data transmission in the implementation of IoT projects, both in edge and cloud computing, as well as the practical determination of the range of sensor data transmission between microcontrollers for each proposed option. A short range wireless sensor network uses edge computing to display information within the reach of edge devices. So, when implementing the project of a home weather station, it is not necessary to require access to the global network. The transmission of temperature and humidity measurement data can be carried out using communication protocols of wireless sensor networks over a short distance. We developed a project of a home weather station using an ESP32 microcontroller and a DHT11 sensor. The results of this project are right now shown on the screen. Data transmission of temperature and humidity measurements was carried out by the Bluetooth interface with display on the mobile device in the serial Bluetooth terminal application. I'd like to point out that the maximum range of communication between devices in the room was up to 30 meters. As said before, a home automation system of any standard can work completely locally without access to the internet, which eliminates delays in the response of smart devices to events. The project of a home weather station was implemented using Bluetooth without access to the internet. Here is another example of a project that can work completely locally using ESP-NOW technology. This technology, developed by Espressif System, can also be used for two-way forwarding of data packets between controllers. It is based on a simplified Wi-Fi protocol. The results of distance measurement transmission between ESP32 controllers using ESP-NOW technology right now shown on the screen. The distance was measured by an ultrasonic sensor. The distance itself was calculated in centimeters on the edge device. Received data was displayed on the laptop screen. During the practical implementation of the project, it was determined that the range of data transmission is up to 100 meters. When it comes to implementing projects not only locally, there is a need to have an access to the internet, of course. Transmission of sensor data to a server, cloud service, or edge user can be done through a gateway. This approach we use to implement indoor air quality control project. Measurement data from indoor air quality control sensors were transferred to a gateway using NRF24 LO1 transceivers. A DHT11 digital sensor was used to measure temperature and humidity. An MQ2 analog sensor was used to determine the concentration of hydrocarbon gases. The edge computing of measurement data was carried out in the ESP8266 microcontroller of the transmission part of the radio line. In order to read digital data from the DHT11 sensor, a library supporting the SDA interface was used. The gas concentration was determined by the voltage at the output of the MQ2 sensor. The built-in 10-bit analog-digital converter of the ESP8266 board was used to get digital measurement data of output voltage. The relative internal resistance of the sensor was calculated based on the measured voltage. This resistance value was used to estimate the gas concentration value based on the calibration characteristics of the sensor. The temperature, humidity, and gas concentration values were sent to the transceiver through the SPI interface. At the receiving end of the radio line, from the output of another transceiver, these values were input to the ESP8266 microcontroller, also via the SPI interface. It is important to emphasize that each of these edge devices at least performed operations of both reading and transmitting measurements of sensors. On the same controller of the receiving end of the radio line, a gateway was created for transmitting gas concentration, humidity, and temperature measurements to the cloud service ThingSpeak by connecting to a Wi-Fi access point. The change in measurements of air quality control sensors at a certain time interval, which was output to the ThingSpeak, is right now shown on the screen. Often, there is a need to organize a gateway for access to the global internet network several kilometers away from the sensor network. In this case, the LoRaWAN network protocol can be used for data transmission. This protocol has low energy consumption and uses LoRa broadband modulation at the physical level. The calculation of the range of LoRa radio line is carried out for the real sensitivity values of the RFM95W receiver. The use of the Okamura-Hata radio wave propagation model is proposed in order to estimate the total signal loss in the LoRa radio line. Typical values of LoRa modem parameters for the frequency of 868 MHz are given in Table 1 and right now shown on the screen. The result of calculation of the communication range and data transmission speed on the LoRa radio line for the value of coding rate 4/5 are shown right now in the Table 2. As can be seen from Table 2, increasing the value of the spread factor of the radio signal, SF, leads to increase in the communication range with a simultaneous decrease in the information rate of data transmission. The obtained values of the radio line range make it possible to more accurately determine the wireless sensor network's coverage area when using the LoRaWAN communication protocol. Right now, we live in the era of wireless technologies and AI is evolving rapidly. Today, it is important to keep abreast, to track trends, learn new things, and adopt practices. Thus, we wanted to share with you the results of our work, which showed the possible options for wireless data transmission during the implementation of both short and long-range IoT projects. The range of sensor data transmission between microcontrollers was practically determined for each proposed option. The air quality control project showed the essence of edge computing with combined use of digital and analog sensors. The data transmission of the air quality control system was carried out through a gateway to the IoT cloud service ThingSpeak. This service made it possible to graphically display measurements that you were actually able to observe today. Thank you for your time and attention.